I'm going to do my best to give you the extra help for balancing chemical equations. And again, um, I'll try to explain everything I did in class with the intention that you can play this over as many times as you need to. And I'll go over the basics again. The reason you balance a chemical equation or you balance a chemical reaction is because everything follows the law of conservation of mass. So law of conservation of mass basically means that matter cannot be destroyed. Matter cannot be destroyed, nor can it be created. So pretty logical sense, like if I have a matter like this here, it's a cup, it's a paper cup with a cute Tootsie smile. So this cannot just disappear into thin air. Like if I need this to disappear, it shows up somewhere else. Even if I were to like cut it into pieces, it doesn't really ever go away. If I were to burn it, it does not really ever go away. The things do not just disappear, and things do not just appear out of nowhere. So the fact that this is here is because there was a tree that made cellulose. Somebody turned that into paper pulp and turned that into glass. So it's a very simple thing. I mean, without it, I would go crazy personally, right? Like, where are things coming from? Where are they disappearing to? Where the world would be a very, very unexplainable place. So when you do, before you do before I kind of get into this more, I just want to get into an example. For example, if you want to start, let's start a chemical reaction. So something very simple, a synthesis reaction, for example, where you take uh, two hydrogen atoms in a diatomic molecule. And the reason I write H2 is hydrogen is one of these diatomic. It naturally comes or exists as a diatomic molecule. With that, I get oxygen, which is also a diatomic molecule. And when I fuse them, or when they fuse together, they form something called fuse is a wrong word. When they combine together, they form something we know as dihydrogen monoxide or good old water, right? So good old water, the right reason I write that as a gas is because this is a very highly exothermic reaction, produces a lot of heat when you do this. So that heat turns or evaporates the water. Okay, so having said that, this reaction is it's a very simple, straightforward reaction. It's a synthesis reaction. You get something called A, you react it with B, and you get a product, which is a combination of both. What doesn't make sense is when you count the atoms. Okay, so I'm gonna take this paper and put it aside, and I'm going to get you to one more time focus on counting atoms, how to count atoms. So if I write H2, the 2 is a subscript. The space to the left of it is something called a coefficient. So anything is like, an atom X has a coefficient and it has place for a subscript. So the coefficient multiplied by the subscript, it is what gives you the number of atoms. If there's nothing written, that means it's 1. So if I have 1 here, 1 times 2 means 2, right? So 1 times 2 is 2. So I am looking at 2 hydrogen atoms. If I am looking at H2O2, which is hydrogen peroxide, and there's nothing there, that means it's 1. So this 1 applies to both the hydrogen and oxygen because it is written in front of a hydrogen peroxide molecule. So I've got 1 times 2, 2 hydrogen atoms, and I've also got 1 times 2, 2 oxygen atoms. Okay. When you have something a little bit more maybe complicated, like if I have magnesium chloride, this is the formula for magnesium chloride. Again, look at the subscript. There's nothing under magnesium, that means it's 1. There's nothing here, that means it's 1. So for magnesium, you have one atom of Mg, and you have 1 times 2 atoms of chlorine. Okay, so once you are able to count atoms, you're able to balance chemical equations easily. Let's get with something, maybe let's try with something a little bit more complicated, maybe something involving like a polyatomic ion. So I've got magnesium hydroxide, and this is 2 that applies to the hydroxide because the magnesium has a charge of 2 plus and hydroxide has a charge of -1. When I cross charges, the 1 becomes the subscript for magnesium and the 2 becomes the subscript for hydroxide. And because this 2 applies to the totality of this polyatomic ion, the entire, you have 2 hydroxides in total. Okay, so again, you got to go with this. If there is 1 and 1 is a coefficient, 1 is a subscript for magnesium, you have 1 magnesium. This one also applies to hydroxide as well, because this is written in front of the entire compound of magnesium hydroxide. So you're going to take the 1, you have to figure out how many oxygens and hydrogens there are. So this is 1, and there's, in a bracket, there's 2 outside, all right? So it's just like mathematics. If you write 4, and then you say multiplied by 3, that means it's 12. If you write 1 plus 3 multiplied by 2, that means 2 and 3 both get multiplied by 2, right? So you have 2. What it becomes is 2 times 1 plus 3 times 2. Okay. So similarly, if you have 1 magnesium, you also have to figure out how many hydroxide, how many oxygens. I'm counting atoms. So I got to go oxygen atom, there's 1. 1 times 2 is 2 times 1. So 1 times 2 times 1 is 2. So I've got 2 oxygens, and I have an identical number of hydrogen molecule. Hydrogen atom, my bad. Okay, so once you know how to count atoms, you're good. You're more than halfway there. So maybe let's try for something else. You got magnesium sulfate. I'm not gonna put, even if I put a bracket, there's no need for me to write anything outside the bracket, because there is no subscript that applies to sulfate as a whole. But if I write the coefficient 3 over here, so you have to see what it does to each element in terms of number of atom increase. So you've got 3 times 1 magnesium, you've got 3 magnesiums, you've got this 3 also applies to sulfate, so 3 times 1 sulfur, which is 3 sulfurs, and you have 3 times 4 oxygen, which is 12 oxygens. So once you count your atoms correctly, you are, you got it. You're on the right path, you got it. Okay, so I was going to demonstrate with some water molecules, and I'm going to try to do this. So in a chemical reaction, you're basically given, where did my paper go? So if I have something like this, I write my reactants on the left side, meaning I'm using some things to make something, right? So that's my product. Whatever I write on the right side, that's my product. So in this case, I want to make some water, okay? So here is a water molecule. I'm going to turn it sideways to see. Okay, you've got a water molecule, which is H2O. So these 2 white spheres represent hydrogen, and the red sphere represents oxygen. So I've got 2 hydrogens, and I have 1 oxygen. This is my product. So I put an arrow and I say this is my product. Now, what I need to make water is basically oxygen and hydrogen, right? So whatever you have over here, obviously you use the ingredients for that to make that stuff. So because I have hydrogen and oxygen, this is what I must have used. Okay, now we know we've learned that oxygen exists as a diatomic molecule, meaning there's two atoms stuck as one. Same with hydrogen. I'm leaving the states out because that's not relevant yet. So what I'm going to do is put an oxygen here. This is an oxygen molecule. And I'm going to put a hydrogen molecule. And I'm going to see if, if all my atoms are balanced. So whatever atoms I start over here on the left side has to equal to, the atoms on the other side. So first of all, I've got 1, 2, 3, but I kind of started with 4. So there's something missing. But I can't just, as I told you in the beginning, you can't just have matters disappear. So something seems to have disappeared, which is, in this case, I have an oxygen missing, right? So I need to have an oxygen on this side as well. So the only way I can have an oxygen over there is as a water. And I believe I had another, yes, I do have another water molecule. So in this case, the only things I have here are water. So water comes stuck to 2 hydrogens, right? So I kind of now figured out where my missing oxygen went. I've got 2 oxygens and I started with 2 oxygens, so that's great. So, but I have to now put this coefficient in front of the 2 over here, meaning I made 2 molecules of water, okay? But if I add an extra molecule of water, what I'm doing is I'm increasing the number of hydrogens as well, right? So count your hydrogens. You got 1, 2, 3, and 4. On this side, I only have 2. The only way this makes sense, right? You can't just like, where did the other 2 hydrogens come from, right? So it would only make sense if you started with 2 molecules of diatomic hydrogen. So once you kind of like, keep things the same on both sides, it supports the law of conservation of mass, meaning nothing disappeared while this reaction was taking place. So this is straightforward. Not all reactions are, visibly, visibly clear to see, but we do what we can, okay? We do what we can with the understanding that theoretically there is no loss in things. Okay, so maybe I'm gonna, maybe we'll just balance one more reaction, and hopefully that will help. So maybe let's take a look at methane. So I have methane, which is C, 1 carbon and 4 hydrogens, and I burn it in the presence of oxygen. So this is a hydrocarbon, it's a fuel, it's methane gas. I burn it in the presence of oxygen and I release CO2 gas as well as water vapor, okay? Now, an easy thing to do, or when you're starting and you are practicing, the best thing to do is kind of create a table. So I like to have 3 columns. And over here, I'll write my elements that are involved in this reaction. So my elements involved in this reaction is carbon, hydrogen, and oxygen. All right, so I've got carbon, hydrogen, and oxygen. And I will I'll label my columns as reactants and products. So the number of atoms have to be equal on both the reactant side, which is the left side, and the product side, which is the right side. So I'm going to go take a look at my reaction to see how many of what we started with. So it looks like we started with 1, remember, subscript coefficients. You got 1 and 1, so that's 1 carbon on the reactant side. So write 1 over here, and then I've got 1 and 1 here again. So 1 times 1 carbon on the product side. Carbon looks like it is balanced, okay? So I don't have to worry about carbon. I'm gonna go back and see what else is there. So I can see that I have 4 hydrogens over here, right? So 1 times 4 is 4. And on this side, I have 1 times 2. So I have 2 on the product side, I have 4 on the reactant side. So I'll go 4 and 2 doesn't make sense. It seems like 2 hydrogen atoms got, disappeared, which we can't have. So this needs to turn into 4. They need to be equal. In order for this to become 4, you need to put a 2 here. If you put a 2 here, 2 times 2 becomes 4, right? So your carbon is not balanced and your hydrogen is, I'm not sure if you see this. Actually, this would make things a little bit better. Okay. So carbon's okay, hydrogen's balanced. We have to now balance or check for the oxygen. I have 1 times 2 oxygen. And over here, I'm going to have to count all my oxygens. But before I do that, let me write what I have on the reactants. I have 1 oxygen. And over here, I have 2 oxygens here. And I have 2 times 1, which is 2. So I have 2 plus, sorry, I have I have 2 oxygens here. And I have 2 plus 2 on the other side. So 2 from carbon dioxide and then 2 from the water, which is a total of 4. You can't have 4 and 2 on the other side. So you also, if this is 4, you also have to turn this into 4. And to do that, you will have to put a 2 here. If you put a 2 here, 2 times 2 is what gives you 4. So now, once you do that, all your atoms seem to be balanced, and you've got a balanced chemical equation. So, I mean, I understand whatever we were doing in class, maybe it was a little bit more complicated than this, but this is a good way to maybe, this is a good way to get started with the basics if you want a little, maybe just an extra review with the basics. And if this helps, maybe, just let me know. And yep, have a wonderful weekend, and I'll see you Monday.